An ice skater skates around a circular rink with a radius of 10 meters. If it takes her 12 seconds to go around the rink once, what is the coefficient of static friction between the ice and her skating shoes? Assume that the maximum static friction supports the circular motion. So, if I draw this, it will look something like this. With this being the ice rink, this being the skater. Now, assume that this is the center, so this will be the direction of the static friction. Because the maximum static friction supports the circular motion, which means that it's helping provide which means it's basically providing the centripetal force needed to keep the skater in a circle, keep the skater moving in a circle. So the free body diagram will look something like this, where you have the normal force acting on her, mg, or the force of gravity, mg. And then here, pretend that this is towards the center of the rink. You'll have the centripetal force, or the maximum static friction. And this is in the radial direction. This is radial direction. It's probably a little too small to write, but for here, that's the center. That's going to be the center of the circle in these two drawings. So, we know that the angular velocity of an object is equal to 2 pi over the period. So that is simply equal to 2 pi over the period. And the period is equal to 12 seconds, since she takes 12 seconds to go around the ring once. So 2 pi over 12 seconds. So this simply becomes pi over 6. And this has units of radians per second. So the angular velocity is pi over 6 radians per second. And I'm not going to simplify that yet. I'm just going to keep it in this form. So the angular velocity is pi over 6 radians per second. Now, we also know that the centripetal acceleration, or radial acceleration, is equal to the radius times the angular velocity squared. Or you can also say that is equal to v squared over r, where v is the linear velocity, but we can replace it with r by the identity v equals rw, or the velocity is equal to the radius times the angular velocity. Oh yeah, and I misspoke. This is actually not a w. This is omega, the Greek letter omega. So the linear velocity is equal to the radius times the angular velocity. Plugging that back in, and that will yield us this equation. So now, just plug in the radius of 10 meters and the angular velocity we calculated earlier of pi over 6 radians per second. Square that. So the centripetal acceleration is going to be equal to 10 pi squared over 36, which is 5 pi squared over 18 meters per second squared. And again, I'm not going to simplify this just yet, but that is our centripetal acceleration. So our centripetal acceleration is 5 pi squared over 18 meters per second squared. So now, if we look at our free body diagram, we can use Newton's second law, which says that the net force acting on an object is equal to its mass times acceleration. In this case, we're going to look at the radial direction, pointing towards the center of the rink. So the only force acting is the force of static friction, or rather the maximum force of static friction, since that's helping support the circular motion, providing the necessary radial or centripetal acceleration. And that is equal to the mass times the acceleration, where the acceleration is the centripetal or radial acceleration towards the center of the circle. So the force of static friction, the maximum force of static friction, is equal to the coefficient of static friction times the normal force, where the normal force minus the force of gravity is equal to the mass times acceleration in the vertical direction, which is simply 0, since the ice skater is not falling through the floor or being pushed up. So the normal force is simply mg, or the weight of the skater. So you can substitute the normal force with the skater's weight, or mg. So the maximum force of static friction is the coefficient of static friction times mg. So we can substitute that into our first equation. And that is equal to the mass times the centripetal acceleration. So now both masses cancel. We get that the coefficient of static friction is equal to the centripetal acceleration over g. Okay. I'm going to erase the free body diagram since we don't need it anymore. So now we just need to substitute everything in. So the coefficient of static friction is equal to the centripetal acceleration divided by g, gravitational acceleration, which when we calculated the centripetal acceleration or radial acceleration earlier, it was 5 pi squared over 18 all over g, 9.8. This simply becomes 5 pi squared over 9.8 times 18. And simplifying this, you'll get 0.28. So the coefficient of static friction is equal to 0.28. And that is how you would solve this problem here.